Hey, Aaron, can you hear me on the Zoom?
I can hear you. Yes.
You can hear me, but I can't hear him. Oh, weird. Because it didn't, when I put to record, it didn't. Let's see.
I heard it. It's quiet.
It was really quiet, though. Let's see.
Is the volume on the computer?
Is it, let's see here. Oh, yeah. Yeah. That's it. Thanks.
Oh,
That's
that's
exciting.
just the speaker, not all set to.
Not what?
It's loud.
I think that's the
for
thing.
the recording.
Yeah. The recording's okay, I think.
Professor, can you
Yeah.
put the recorded video in your homepage about September 14th? That's not right.
It's not there.
Yeah,
Yeah, there's one there. And you go there to can't find it.
Okay. I'll have to fix it. Is it under solutions?
September 14th, right there.
Oh, yeah.
Then you click there. Nothing.
All right, I didn't put I have it recorded, I didn't, yeah, you gotta email me when that happens, I mean, actually, can you email me like now, and then when I look at my emails, I'll see it and I'll fix it, because I'll forget, like, I'll totally forget about it. Yeah. But, yeah, I just forgot to post it up there, sorry about that. That would have been helpful, because you weren't here on Thursday, right? That would have helped you. You gotta email me.
And sometimes there was some link and web page in the wrong web page letters.
Mhm.
There's some kind of vacancy. In the case of the September 13th, there is a vacancy of your ID in the address. When I fix that gets worse. So
What is it again? Like when this,
Yeah.
oh, you mean down here?
no, that
This?
yeah, then you click. There's a web page on the upper side.
Yeah.
Yeah, and there is the last part KP5.
Oh, yeah.
And before
Okay.
that, there is some kind of ID address.
Oh, yeah. You know what this is? That's a YouTube code. Like, I think if you can go to like YouTube, that's a code for a YouTube. And I didn't put in, it has to have a little phrase in the front that makes it go and play the video. So it's a YouTube video. I don't know if you can go there and somehow put in the that code number. Anyway, I can fix it, but I didn't put in the thing in the front. It's got the YouTube address, but it doesn't have the let's see, if you search YouTube, I wonder if you can just put that number in. If it just goes there. Yeah, that's it. It's right here. So that's Thursday. I just forgot to put there's a little phrase that goes like quote, and you put like view. And
Like ID and manage.
yeah, that's the code. When you see some weird number thing like that, that's a YouTube code. But you won't see it again, but basically that's what that is. But like that's the ID for this YouTube file. It's weird, like YouTube lets you put any amount of video up. There's no limit. I mean, like if you could put all your data files into YouTube, into video format, you could store unlimited amount of stuff there, I mean, it's just kind of weird. It's like terabytes of nice stuff up there. It's never complained. It's like, whereas Zoom eventually tells you like you got too much stuff. Plus YouTube's easier it does the captions and all. It's like easier to work with. We got to figure out a way to make money off it though. I haven't figured out that. Like somehow you can make, I don't know if you actually get money from it or what, but some people do. Anyway, this homework wasn't too good, but basically though 12 people have an A right now, and 14 have a B. So it's everyone's in good shape, I think. I'm just going to give a solid A, solid B. So if you have a 90, it's an A. Like you're done when you're at a 90. And if you have an 80 and you're not going to get over 90, stay at the 80. You know, so it's kind of like it's just going to be a solid grade. So anyway, everyone's in pretty good shape, I think. I mean, some people at the bottom of B, and if it looks like you turn the corner or something, I guess I could kind of compromise a little bit, you know, but basically it's going to be hard to dig out a solid like an 80, right? Because 3/4 of the semester is still out there. Anyway, you can see how it goes, but the grades weren't good on this one. I mean, everyone got above 70, I think, but anyway, so it wasn't that easy to do. When I teach the undergrad thermo, we go through like what a correlation function is briefly, you know, for like half a class or something. It didn't sound like anybody had ever heard of it before. I don't know. Anyway, so it says like, what's a correlation function? So let's see. I actually had some notes on this stuff. So yeah, so binary, people said, I think half of you said like binary meant you had like A plus B, like a mixture of something copper and zinc. But that is a binary mixture, that's true, but it's not a binary correlation function. So binary, so anyway, I can see how that's confusing. So the binary, for the correlation function, the binary means you have two positions, like you have some stuff. So it can be just one component, you know, it can just be like some kind of component. Right. And then so binary means you can have 2 points, like binary, two things that are interacting, like point I and point J, and they're separated by this vector I. Right. So binary means two, but it means two positions. That's why you get G11, R, G12, R, and G22, R. Otherwise, you would just have G12. So G11s means you're looking for like XX, G22 means you're looking for like OOs, and G12s means you're looking for like OXs or XOs. There's two ways to do the 1, 2. Right, so anyway, I can see how you get confused about that, but hopefully that's.
When I search about that, I got the keyword on another keyword, radial distribution function.
It's the same thing, yeah. It's the same.
Please use the more common words.
I mean, correlation function is pretty common. Binary correlation, the binary word is what got people, but it's called that. It is called that.
It's also called pair correlation.
Yeah, it can be a pair. Pair would be like same as binary. Pair is clear, right? Pair means is
the radial distribution function is a type of binary.
Yeah, just type of binary. Only when there is composition, radial distribution is binary.
I mean, all right. I realized, so it's in the undergrad book, and we cover it in half a class. We never say like why. In other words, conceptually, it's a useful concept. So there's only two places where you use it. Well, there's other places, but basically the main use is in simulations. Because when you do it in molecular dynamics, you stick the stuff in, it cooks, it moves around, and you end up with something. Then what do you do with it? Like, because when you do the Monte Carlo, every cycle, every time you change anything, you calculate the free energy. So you have the free energy straight up in the Monte Carlo. That's what you're calculating every time. If it lowers the free energy, you keep it. If it raises it, then you roll the dice. Right? So sometimes you keep it when it goes up so you can escape. You can go over energy barriers and things. Otherwise, if it just took it only when it went down, everything would collapse into just a solid chunk, because that would be the lowest free energy, and that's not. It doesn't have any temperature effect on it. So temperature makes things like loosen up. Right? So Anyway, so for Monte Carlo, you don't need a correlation function. You get a free energy straight up. Every time you do it, you calculate the energy between every pair of everything in the system. And you sum that up and you get the free energy of the system. That's kind of, and then you use that to judge whether you accept that change or don't accept that change. Right. So Monte Carlo straight up gives you the free energy. If you do molecular dynamics, so each particle has its little velocity and its acceleration, and then all the potentials that it interacts with. So it decides like where it's going to go, like a pool ball would decide when it bounces through the pool table or whatever, bumper pool. Right. So, or the collisions and all. So it just does a calculation for every particle. So there's like a time step, everything moves with the velocity and acceleration you put in for each particle. And there's billions of particles. And then they move, and then you calculate like all the what the response is going to be, like the force times, you calculate kind of the energy for each particle of how it's going to end up changing the velocity. The particles is dynamics. So you're looking at the motion. So you just let it cook with, it's just as if it was a real atom, and what does a real atom sense when it moves around, and all the rules you know about real atoms moving, like you put that in and just let it move, right? So you just let it go. It's like a natural, it's kind of like you're making nature in the computer, and it just goes ahead and does it, right? So someone's locked out. Anyway, so yeah.
So Monte Carlo, the delta G, they calculate that just from pure statistics?
No, you calculate the actual value. So say you did it on a grid, right? And then if you have a potential function, and if this atom and that atom are that far apart, you have a potential, like a 612 potential. It gives you the energy of those two atoms, their interaction energy. You calculate, and you randomly move the atoms. So there's no like drag coefficient. So in this case, he's got a molecule. So he's also got this idea that the molecule can rotate, and the energy of the molecule changes when it rotates. So you have a rotational, so you have translational motion, you have spinning motion, and you have bond rotation motion. So in the Monte Carlo, that Minnesota thing, they have all those steps, all those possible steps, and they're all going to change the energy of the whole system. Like the free energy of the whole system changes every time one little thing moves. If one thing moves here, then the other guy's energy changes, and that energy changes some other guy. Okay. So everything's interactive, but you can possible to calculate the entire energy for the whole system. Like a billion things, you can calculate the energy of it. And then you say, because of that move, that one move, did the energy go up or down? If it went down, that's great. If it went up, roll the dice. And sometimes you're going to accept it, sometimes you won't. The amount you accept it depends on the temperature. The higher the temperature, the more you accept. And that allows you to get over energy barriers and stuff. And to find, so it ends up looking just like normal, like what you'd think phase separation would look like. Like the if you do icing model in Monte Carlo, Metropolis method, you can get an app for your phone that does it. Does like a phase separation, change the temperature, and it phase separates. I have it somewhere on the web page, but it might be more fun to find it if you want to. Anyway, so that's the difference between the two. Like they're different. They're quite a bit different. They get almost the same result, but they're different, right? And the experiment is kind of similar. So that means that's good when they're all the same. What else was I going to say? So if you do the molecular dynamics, though, you have no free energy, you have no like nothing. You have nothing, you just have a picture of the system. That's it. You can have a movie of it moving around. You can see that it forms phases, like one of the things he shows, if phase separates, things like that. So that's qualitative. But what you really want to get is like the free energy, so you can tell like what's going on, or the density, things like that. All right, so you can't get that, so you have to use some kind of statistical tool to get it. So you have a picture of the thing, and then what is the free energy of it? So you calculate these correlation functions, right? And then from those, you use that per whatever. What's the first guy's name? First guy's famous, the second guy isn't. I remember the second one, Burr. Anyway, so you use that something Burr integral, and it integrates like. So the characteristic of these is they're basically like the density over the average density. So when R gets very large, you reach the average density, so that thing's going to go to 1, right? And then it'll go up, and then possibly, depending on which one it is, if it's 1, then it's gonna it'll go to 100% with 0 also.
Page number, so.
Oh, sorry,
um,
I don't know why that guy. Anyway, so 0's down here. So at infinite R it goes to 1. So you take G minus 1 is like the thing you're looking at, so that this thing becomes like a factor that goes from 0 to 1 instead of like from 1 to some other number, right? So that's where the -1 comes from. You integrate that thing. That gives you this capital G, which is called the oh, I can't remember the guy's name, something Burr integral. Kirkwood Burr, yeah, thanks. Kirkwood's rolling around in his grave, so it's like Kirkwood Burr, the KB, whatever. So that's that capital G. So that's not the Gibbs free energy. So I think someone found a paper somewhere where they call that the JIJ instead of the GIJ, which that some other symbol would make more sense because the main purpose of the Kirkwood Burr G is to get the actual G, the Gibbs free energy. That's kind of what you want to use it for. Right, so calling it G is a little bit confusing terminology wise. Right, so anyway, but that's what they call it in the paper. It seems like most people using this G for the Kirkwood Burr. Then in the paper, he actually calls it the KB something or KBI instead of calling it G, because it would get way too confusing in the text, right? So anyway, so you can see they need a different symbol for that guy. So then you integrate it. Then you take the G's and there's a function that will convert it to the free energy. See, conceptually, you can kind of see that the way the things are packed together is impacted by the potential mean force is kind of what they call it. It's like the potential as you move things apart. What's the plot of the energy of the two, and then that affects the packing, and that's basically giving you kind of the free energy of the system somehow. And Kirkwood Burr figured it out. And it doesn't seem like anybody really explains it very well. I mean, not to my understanding, but maybe you guys can figure it out. But this, if you want to figure it out, though, this book by this Israeli guy, right? His name Naim, but there's also a book on entropy if you're interested in the philosophy of thermodynamics. Yeah, you have to put it. Well, you have to put an F at the end to get the book. Like the web page has this, like all the books are like this, .pd, and you have to put an F at the end, and then it'll get you the book.
Yeah.
That's the trick, right? So anyway, that seems to work. Unless you have, if you have Unix, if you're using Unix, it just goes directly. Unix doesn't use .pdf; it just figures out it's a PDF. So if you're using Linux or something, it'll just go there. But no one uses Linux except people.
So the package of this F is your intention.
Yeah, that's to. Yeah. So yeah. So anyway, that's a so if you're using DOS or Mac, you have to put an F on the end. If you're using Linux or Unix, apparently. So anyway, so if you look in that, like page 83, so so he goes through like the correlation function, how you get things from it. Basically, the first thing he gets is the pressure, and then he uses so he calculates the pressure from it, and then from the pressure he gets, because PDV is going to give him the Helmholtz, and then he gets the Gibbs from the Helmholtz. So he goes through that in sequence in here. But the first thing if you want to see how you get the free energy from the correlation function, the first step is to get the pressure, which page 83 does that. And then he goes through the whole 9 yards of it here. I mean, it might be interesting to look at, but it's not really necessary, but basically you can look through that section. He actually has a chapter, I think it's on page 111 or something, where he says like, so if you want to know about correlation functions, this book is pretty good, but basically, unless you're doing computer simulations, you might not need to know about correlation functions. The other place you need them, you might see them is in see thermodynamics from distribution functions. That's section 105 is basically answers question 1 if you wanted to, but it's a book, so you couldn't really put that in the answer sheet. So anyway, the other place for correlation functions, it's the the Fourier transform of the correlation function is like the diffraction pattern. So if you, so that's the other, there's a couple other, but basically simulations is the main one. Like you're stuck, you have molecular dynamics, it's easy to do, plug and play, you let it cook, it comes out with the answer. Then what do you do with it? So then the next step is get a correlation function. So it's a way to get an answer from like this kind of video game kind of thing, in a sense. I mean, it's nice to see a movie of the molecules moving around. You can kind of believe it to get the right density in the end, but basically to get numbers from it, you need correlation. So if you take like G of R, so G of R for something like a crystal is going to look like, oh, there's a thing I have, they're like 0R, and then if I'm going through some kind of crystal, then I see it again, right? So it'll be a bunch of spikes. It repeats. It's a bunch of delta functions. So basically, Fourier transform involves, and then the ones we're looking at are just like 0 and going like that for like a 1, 2, or starting at 1 and going like that for a 1, 1. In other words, when you're at 1, you can see 100% 1. Then you go to the density, average density out there, right? So anyway, that would be like a 1, 1, a G of 1, 1, and G of 1, 2 is going to have this like hole here, like a correlation hole where there's a region where, because you have 1, 2 can't get to it. So there's some kind of area, excluded volume, right, between the two. So anyway, so if you have the correlation function, you can, so the Fourier transform is going to superimpose sine waves on that. Like say I could make a series of sine waves with different frequency, and then I could sum up in different amplitudes, and I could sum up those sine waves. So sum of those sine waves, Q is kind of like the angle, the scattering angle, and R is this R in the system. So if I could sum up those sine waves, then I could recreate the correlation function. So you can create any function from a series of sine waves. That's the Fourier theorem. Any function you have, any function in the world can be decomposed in sine waves, any noise pattern, right? So then you take the amplitude. So instead of talking about R, you talk about like inverse R, which is this Q thing. So you call it inverse space, and Q is basically the angle, scattering angle, and then they can plot like the amplitude of those sine waves. So the amplitude of the sine waves, actually the amplitude squared, but versus kind of the angle, and then you can get the diffraction pattern. So the Fourier transform function of a delta function is a delta function. So that transforms directly into like spikes, so diffraction peaks, right? So, and then Fourier transform of these other shaped curves end up being some other shape thing, which you can directly measure. And you shoot a beam of X-rays and neutrons or light through some stuff, right? And then you collect what comes out here. Then you measure the angle here, either called theta or 2 theta. So diffraction calls it 2 theta, scattering calls it theta. Then you pick up the intensity here, which is equal to the squared amplitude of the Fourier components that you got out of it. Right. So very simple experiment. The first thing you do is like, I have a laser, I'm going to point it at a cat, and then it's like, oh, what comes out, it like scatters off. And then you measure that with some kind of detector. Then what do you do with it? Well, originally nothing, but then they noticed like von Laue and these guys were medical technicians of World War I. They noticed when they shot it at metal, like he had a ring on, they get spots. And they figured out the math of where those spots came from, and they realized it was a Fourier transform of the correlation function. So these guys were thinking on kind of a higher level than your normal medical technician, but they were taking anybody in World War I, It's like even the physicists got put into ambulances if they didn't want to sit in a trench and get whatever happened in that movie. All Quiet on the Western Front, but which is a pretty good movie. Like it just came out, but it's pretty depressing. Everyone dies in the end. That's how it works. For no reason too. It's like pointless death. But anyway, it was supposed to be an anti-war movie. So tell you what a binary correlation function is. Prefab reported parameters from binary correlation functions. So I just wanted you could have just spit out the equations. He gives the equation for it, he just gives the equation, which is about the level of understanding that I think he has, like, oh, I can get the chemical potential as a derivative of the free energy from these G's, Nobody, I mean, Beam in that book explains where this function comes from, but I think no one else really, there's not a simple way, I don't think, to say like what this has to do with the chemical potential. I mean, so just the equation, they're related, or you give some kind of hand waving thing about the things are moving around and it's a free energy somehow, blah, blah, blah. Right, that's about all you can do with it. But basically it's some equation, right? So, and everyone just spits, if you read the papers, this comes up pretty often, like if they're doing like the dynamics, everyone uses this equation. So you'll see this equation like repeated over and over again. It's in the books, it's in the papers. So anyway, so that's kind of that business, right? That's that question. So everyone lost points on this question, I think, mostly. And then people like not understand the difference between Monte Carlo and molecular dynamics. At this stage, I think it would be good to know the difference, between the two. Because you see, they're comparing these two things that are completely different. I mean, they both use a computer, right? But they're completely different. So, I mean, some rough idea what the difference is pretty useful, right? So we'll go through it more. Like there's a section just on simulations at the end. We'll do some simulations, but basically, it's good to know the difference between those two for thermo, because those are the two like main bread and butter things. The problem is there aren't a lot of papers. There's some papers on experimental thermo, but most of the papers where they're actually dealing with the things we talk about in the class are simulation papers. Because it's just, you can't understand the simulations at all if you don't have the thermodynamics thing. Whereas the experiments, you can always, kick the dog and listen to it bark. But basically, to understand how the dog works in a simulation, you have to really understand the fundamental rules that apply to the game, right? So that's why I guess there's nothing you can do with a simulation without the fundamental. It's just like you can watch the movie of the things moving around, but you can't. It's not going to give you anything you could publish, So basically, simulation and thermo, the theory part, go together hand in hand. Whereas experimental, you can always get by with, I made a better widget, and that's a paper. So you don't have to necessarily understand why it's a better, you have to show it's a better widget, but you don't have to say why it's a better widget necessarily. Right? So, I mean, people, if you can make money on it, people will be interested in it. So, okay, so that's A. Any questions on that thing? I think that's a really important question, but basically everyone kind of tanked on it more or less. Yeah.
If I answered about the question A, the last part, first between the Chen and the original one. My answer was the original one is made a simulation depend on the modulus volume, and Chen is made of simulation depend on the modulus weight. I wonder, is it a literally correct or completely incorrect?
Well, no, you're right that Chen's talking about molecular weight. In fact, the paper I gave you I don't think it's this 2018 Chen, right? I think it's a different Chen. So we're doing a Chen, is this really 2018? Yeah, it's 20, but the Chen that he references isn't this Chen, I don't think. So he's saying Chen et al. Is that 2018 or because it seems like it's a different Chen, because this Chen isn't talking about the same thing. It must be one of the first references here, right? Oh, it said right there what it was. Chen et al. 29. A lot of Chen here. 29 Chen. So it is that paper. The paper's different, right? He isn't even looking at the same. He's not looking at the same system, even, I don't think. I think he must mention, see, he's doing PEP, not polyethylene. So it's like kind of like it's polyethylene propylene. That's called EPR, right? Ethylene propylene rubber. So you have blocks of ethylene and blocks of propylene. the propylene crystallizes, the ethylene, if it's small enough blocks, doesn't. So you get rubber reinforced polypropylene. And you can extrude that. So it's a rubber that you can extrude. So you can injection mold rubber parts with it. And it's just polyolefins. It's cheap, but it's anyway. So that's like a popular polymer, but basically that's not the same. He's doing polyethylene without the propylene part. So I don't know what. Anyway, somewhere in here he must say without the propylene to compare it, because he's taking data out of this, I guess, that to compare. He's got the phase diagrams and everything in here. Yeah, so yeah, and he's looking at the molecular weight dependence, right? But I'm trying to, I think I asked, it's like, how does this approach? I'm talking about the approach, like the computer approach. How does this approach differ from Monte Carlo? Monte Carlo, like how does Monte Carlo and molecular dynamics? What's the difference between them? That's what I was trying to ask. So not about the molecular weight dependence thing. That is a difference. It is kind of a difference between the two papers. I can see how you're confused.
Sorry, I repeat my answer. The KD theory made the simulation depends on the molecular volume, and Chen depends on the weight. So it's like my asking about, is it correct or totally incorrect?
That's kind of way I see it. I think that's totally incorrect. That seems to be getting confused with the Florey-Huggins thing in the Hildebrandt business, which is volume and moles. I don't know it. Maybe you could explain it better or something. If you think there's points, just email us up on it or something. You know what I mean? But so you might have some argument for points, but I don't see that was right. Way I'm looking at it, but you might have a different way to look at it. So I'm open to suggestion. Anyway, equation 2 is Florey-Huggins and Hildebrandt. So they're the same thing. Like the point of this question is the two are the same thing. They both, you can get the chi parameter or the Hildebrandt parameter from the del, from the solubility parameter. And both of them you can get from the cohesive energy density. They're the same thing. Like all Florey did was he used volume fraction instead of mole fraction, and then he divided by the molecular weight, because the things that are mixing, like the entropic units, are glued together. So they, it's he just took the mer units, would be too much entropy because it's stuck. So there's two differences. He puts in volume fraction, which other people had done before he did it, and then he does this divide by molecular weight, which is just kind of logical. Like you don't have as many things in the entropic term. Enthalpically, there's still mer units interacting with mer units, but entropically they don't have a mobility, like a freedom of mobility. So the answer should have been like they're the same thing. They're really almost identical, right? So Florey won the Nobel Prize basically for that equation. So whatever you want to put in that. He taught at UC. He taught in the chemistry department at UC kind of before he became famous, and he went to Ohio State for his PhD. So I don't know, he was around here. And then he was in Akron, but he wasn't at University of Akron, he was at Goodyear. So you can go to his office and at Goodyear, they still have you can go to see where he had an office. It's kind of weird. Because Goodyear doesn't do much research anymore, but right. So what's the reason for the difference? I mean, the volume thing is because I think it's got to do with the shape of the monomers, something like that. Like it's shape differences. So they aren't just boxes on a grid, they're like different shapes, different volumes. So somehow volume fraction makes more sense. And the dividing by the molecular weight gives you that the things are glued together. So you don't get as much combinatorial entropy. You don't get as much entropy because you have to divide by the molecular weight. But that's designed for molecular weights of 100,000 or million. And this is molecular weight. I think it's 4 in the paper. I said 12 here. So when you're at 12 and 4, I don't think there's any difference between these equations. Like it isn't a big enough molecular weight to make any difference. So I think there's no difference when you're playing around with things that are so small. So the simulation guys are like, oh yeah, I'm doing polymers, quote unquote, which are 4 long because it's really an organic molecule. And then so because I'm doing polymers, I have to use Florey-Huggins. They could have just said Hildebrandt, but maybe it wouldn't have been popular in the polymer literature. So they published this in I'm not sure what journal, Macromolecules. Maybe they felt like they had to use Florey-Huggins, but they didn't have to. And then Sakai has such a low number of 0.003, so it's positive, meaning it's admissible. So why is it? So you just had to say like the entropy is negative. The entropy term is going to make it admissible. So chi can be positive, doesn't mean that the system phase separates. Positive chi usually would mean the system phase separates, but it doesn't here because it's a small number.
In the real situation, not contrast simulation,
Mhm.
is that chi can be a negative value?
Yes. Most cases it's a negative value. If things mix, yeah. I mean, in most cases of polymers, it would be a negative value if they mix. If it's positive, they don't mix. So there's very few polymers that mix. So in order to get that, you need to have a negative chi.
There was a mention about that when chi is high value, there's on mix, and low value, there's more mix. And what I understand is the low value is approach to T0.
Yeah, well, when it's 0, it's called athermal. There's no enthalpy. So that's like a just entropic system. But it can be negative. So you have attractions. There's a lot. I mean, you can have a lot of dependencies of the Hildebrandt and chi both, like composition changes. When this term can change with composition, change with temperature, pressure, whatever. So you put whatever you want, and chi is like a garbage can. So yeah, because you have this ideal system, the X ln X thing, that's ideal, right? And then everything that doesn't fit into your picture of ideal, push it over to the right, and that goes into chi. So chi is just a garbage can for anything that's going to not fit into that X ln X entropy term. So then it can have non-combinatorial entropy, it can have pressure dependence, anything can happen. So it's initially enthalpic, but basically can be anything, right? So it's a good place to put it because then you still have your ideal thing you can work with easily, and then the other part you can make up whatever you want, whatever function you want for it, if it accounts for the behavior. And then let's see, drive equation 9. I think that we did that in class and everyone got that, I think, almost everyone. And equation 14 is the same thing, it was done in class. It's in the notes, it's in the PowerPoint. This thing, I think everybody got this thing. And then everyone got E too. The thing about I just put that in because it doesn't have to do with thermodynamics. It's like just that order parameter. At some point or other, you'll run into a situation where you have some stuff. So say you're extruding plastic into garbage bags and it has like streaks in it. So how do you say like if the streaks are lined up or not? So literally people use this function to talk about streaks in garbage bags. It's like this is like the universal function for how things orient. 0 to 1. So it's like you can use it as a weighting factor, like one that's oriented, it's 100% strength, and the one that isn't is this other strength. Want to know what strength the thing is that you just extruded, put in that number times whatever the two are, and you just pop out your linear coefficient of strength for it, or moisture permeability, or whatever term you want for it.
So is the equation 22 formula is just expression, there is no derivation?
No, the derivation is a Legendre polynomial. It's a first order Legendre polynomial. It's from the 1700s. It's been derived a long time ago. It's the same as the Legendre transform, Legendre. Yeah, you can Google it. There's a wiki page. I think it might even be linked on the, is it linked on the web page or anything? So yeah, here, Legendre polynomials and orientation. There's some kind of paper on it. P2 cosine theta, that's the one they're using. I guess the second order. First, I don't know. Anyway, you can look at it. It's a first order is 1, second order is this. Third or fourth order, I guess they only have even orders. And then there's a gamma order, which is that. So who did this? Like someone that had a lot of time on their hands. Oh, Legendre. Oh. Laval. Okay, so I know this guy. I know this guy Prudhomme. He's retired now. He moved from Laval to University of Montreal. Anyway, so whatever. He wrote a paper on it, I guess. What journal is this in? Printed in Canada. So it's the Canadian Journal of Chemistry. Ooh. So let me go. Prudhomme's a really nice guy. There's 2 Prudhommes. One was at Princeton. I think he's still alive. As a rheologist, right? And he's a polymer rheologist. And this Prudhomme was at Laval, which is like a French-speaking Quebec, kind of like Quebec City University or whatever. Then he moved to University of Montreal, also French-speaking place. But anyway, French people like French people, which is always odd because I'm like 1/4 French. And then so I don't really identify much with it, but like if you go to New Orleans or like Baton Rouge, and then all of a sudden you get the best hotel room, like everyone treats you nice, and it's really pretty weird. Same in Montreal or like Quebec, you go up there, all of a sudden you're like special, So anyway, so any questions on that? Anyway, everyone did bad on it. There are a couple people got over 100 slightly, but they also lost points on other things. Like if you, like for this ants, like this business, there's a plot of like gamma versus composition in every paper and also in the notes and everything, where it shows like the intercept at 0 gives a 1, and then the intercept of the other one's Henry's law. So you need to just say like Henry's law, Rhodes' law, and show that plot. I gave them like 3 points for that extra because it was exactly the way I would have answered it and the way I would have wanted them to answer it. If you look at even if you look in this, I noticed in this name NAIM, I guess that's how you pronounce it. He's got those plots in this book too, the plots of the gamma. It's in here somewhere. Somewhere he's got the plots of the gamma versus composition, shows the Henry's law and the Raoult's law limits. So literally everyone shows that plot to answer like that question. And one group did it, so I gave him some extra points. You didn't have to, but basically, that was an exact answer. So and someone else got extra points for something else like that. So anyway, so that's about that. Any questions or anything on this stuff? So, right. So anyway, so we got phase diagrams. So this is the eutectic phase diagram. That's like the workhorse, I guess, the bread and butter phase diagram. So the question is like partly like, where does this come from? I mean, in other words, so we've done this ln x thing with some interaction parameter, like entropy, enthalpy equation for mixing of things. And then all of a sudden you get this thing, doesn't look anything like it, right? Nothing to do with it at all. So basically, surprisingly, you can get this thing from exactly that same simple approach. Right? What you do is you're going to write the free energy for each of the different phases in this thing. So in this case, you have copper crystals and silver crystals, right? Both FCC, they don't co-crystal. You can't put the copper into the silver crystal, so they don't make a solid solution. In other words, so it's possible to have a crystal where the copper fits into the silver because the sizes are within 15%, and whatever. There's a couple other criteria that they would fit together into the same crystal, and then you could have like a solid solution where you just throw in as much copper as you want or as much silver as you want and just move across and just have a single crystal structure. And the lattice spacing changes a little bit as you as you change the composition, like brass, right? It's like that. So, right, silver and copper don't do that. Like they don't, the two crystals are separate. They're different sizes. They don't fit together, right? So you can have a free energy plot of silver and like, or you can have a free energy plot of copper. So if you go here, there is some copper in the silver. Like that's not pure silver. If you're at like where the pointer is, if you're here, it's not pure copper. It's got some silver in the copper, but the amount that it can hold is like 10% for silver and like 3-4% for copper until this doesn't fit anymore. Like you have too much discrepancy in the sizes, then boom, the silver precipitates out as almost pure silver crystals. Then you have a mixture, depending on where you are. Like if you're over here, you're going to get mostly copper, right? So you have a matrix of copper crystals. I mean, you're at 90% copper, so it's going to be a matrix of copper crystals. And then it's going to have little precipitates of silver, like little spheres of silver in it. Right. So that's called a tie line, right? So this Q phase and the O phase are in equilibrium with each other. And the composition you put in is P. And the amount of material of copper is going to be like the length of the line OP divided by the length of the line OQ. So you go to the opposite, gives you an amount of that one. So it's got to be that way because this is the bigger line and you know it's mostly copper. So it's got to be the opposite, gives you that. And then the amount of silver is like the PQ divided by the OQ. Right? So that's the tie lines. That's how tie lines work. Those two phases are in equilibrium. The composition you put in, then it's going to separate into these. This region is like no man's land, and it's going to form that crystal and that crystal. The composition of that crystal is like 10% copper, 90% silver. Composition of this crystal is 98% copper and 2% silver. And if you figure out, if you calculate like the amount of silver that I put in, you can account for all of it. In other words, if you add up the amount of silver here and the amount of silver here, you'll get the amount of silver you put in. Right? And the same with copper, like the amount of copper here plus the amount of copper there is what you put into the thing. Right. So that said, it's pretty hard to get that actual thing to show up. Like, how would you do that? If you wanted little spheres of silver floating around in a copper matrix, right? How would you get that? So you mix up some powder, pure copper, pure silver, then you're going to heat it up to 1300 Kelvin, right? Like 1100 C. That's pretty hot. And then you're going to take that and somehow magically jump to this 950 Kelvin. So it's whatever that is, 600 something. Right, 1100 to 600 is a pretty big jump. Like somehow you have to make that jump almost instantly, from the liquid to the solid. So that's called a quench. That's a rapid quench. So somehow, if you had a small amount of it and you could dump it into a bucket that's sitting there at 950 C, you could do it, theoretically at least. There's always going to be some problem because on the road to getting to that, say you did that whole process slowly, right? So you have liquid copper and silver mix. So the liquids mix. They make one liquid phase. Then you cool it down, and then you get boom. All of a sudden you get to the crystallization point of copper for that mixture. Silver hasn't crystallized yet, but you formed copper crystal. So you start forming like a precipitated copper comes out. It's like a snowstorm, crystals of copper. If you're going slowly. And then as you go further, so the equilibrium is between liquid phase and copper, right? And the initial point right here, you're pure liquid. There's no copper. So as you go deeper, you can make a tie line between liquid and you get more and more copper because the length of this line between X and this liquidous line gets larger. And so you get more liquid and less. You get more copper crystal and less liquid. So at this point, when you're at T2, you have like, that's about like 1/5. So you get 20% liquid and 80% copper. So at that point, if you quench from here to here, you have little liquid domains of this composition, here, like 70 42% copper, and then in a matrix of copper that's at like 98% copper, and then a little bit of silver. Right, so again, like the 10% silver that you put in, if you add up the silver and the liquid and the silver and the copper, it adds up to the 10% that you put in. Right, and it can only do that if you have that amount of copper crystal and this amount of liquid. Right, so you can see, like, depending on your processing conditions, so you have an equilibrium phase diagram, and the way to use it is to impose kinetics on it. Like, what's the kinetics of what you did to it? And this is like a map, like if you turn left here, if you turn right there, then you end up in Columbus. But basically, if you don't stop for the stoplight or something, you're going to get just powder settled out in the bottom, and you're not in Columbus, like somewhere else, Dayton or something, right? So anyway, the only way to get to actual equilibrium is to do something so rapid and fast that you get to this point and it just decides to do that. Because if you just go slowly, you're going to get a snowstorm of copper coming out. Then by the time you get here, you have mostly copper, and then the liquid at this point is going to be at this point, which is called the eutectic. So that's the point of no return. Once you cool to the eutectic temperature, there is no liquid anymore. Like no liquid in equilibrium with solid anymore.
No, this is the go to select.
Somebody,
If you really don't want
I can see
it. When I throw it away,
them. Yes. Good. I got rid of her. There. Right. Okay, so anyway, that's how you use a phase diagram. Like, so you get this phase diagram, so eutectic phase diagram, because it has its lowest melting points, you have this reaction. L goes to alpha plus beta. So liquid goes to two solid phases, in this case, silver and copper. And then the equilibrium, the eutectic composition. So the eutectic temperature and eutectic composition. So it's 42%. And then at that point, go directly into these two eutectic crystals. So everything here is labeled eutectic. Eutectic temperature, eutectic composition, then the two eutectic phases that you get from the alpha beta. It's like the generic name of them. Right. And if you go deeper, you get different composition crystals. So you have this Gibbs phase rule is supposed to help with this. Like there's 0 degrees of freedom when you're at this, because you have 3 phases in equilibrium. So 3 phases, 2 components, 2 somehow gives you 1 here. Yeah, that's the 4, that's 3. So you have 1 degree of freedom. Should be 0 degrees of freedom. I can never get this to work right. 2 components, that's true. Number of phases, 3. Should be plus 1. Oh, because there's no pressure. Thank you. Now I know why I can't get this to work. Anyway, I don't use this much, but so this, oh yeah, because you're at isobaric. Okay, good point. You just have temperature you're changing. That does explain a lot. Okay. Anyway, so this will tell you 1 point you have 0 degrees of freedom. Per line you have 1 degree of freedom. Like you can change the composition, everything else is decided. And when you're floating around in these regions, you have 2 degrees of freedom, like temperature and composition. Like if you're in an area here. That's kind of the idea of this. So this is supposed to help you figure out what's going on here. Like, in other words, if you're at a point, then you have to figure out like what's in this thing. So you have to have 3. If you're at a point, there has to be 3 things in equilibrium with each other. Right? So you have like liquid, this silver crystal, and you have this copper crystal. So and if you're at a line, there should be 2, whatever. So you can use this to figure out, and if this is a simple phase diagram, right? So you can get very complicated phase diagrams. So we have let me see if I can get out of this. Oh yeah, and then there's a program on the web page. So ThermoCalc works on a Mac and a PC, and then there's Calc, what is it called? Calfed, Calf something. CalFad. So CalFad does the same thing. You put in the compositions, you can predict the phase diagram of this using the Gibbs free energies that will go through how these are generated, but there's programs that just do it for you. They can put in whatever compositions you want, it'll give you the phase diagram. Let's see, I wanted to show you though, something here. So I wanted to show some more complicated phase diagram. I know there's some in here. Well, there's the high entropy alloys on this paper. I didn't, these are like things I was looking for the homework, but high entropy alloys. So it's the same thing. It's got 5 component, same stuff, right? Kind of 5 component, 4 or 5 component. I think you have to be 5 to be. Anyway, so, and then, all right, so this is what you get. This is a eutectic composition. So when you get to the eutectic composition, you get these weird striped, or you can get needle-like, you can get a variety of kind of tiger skin looking structure out of it. Okay, so eutectic, you can tell when you're at the eutectic, like if someone says, what composition does this thing come from? You are searching for like, this is from a eutectic phase separation. Because at that point, let's see if I can get back to the, this guy here. So at the eutectic, you don't have like a matrix of one and a matrix of the other. You're making like both things at the same time. Right, so you're going directly from liquid to the two things. So there's a diffusion issue. So you're going to have normally fluctuations of copper and silver, regions where they're higher density. And then when you get to the eutectic, all of a sudden it just wants to boom, like go to these two solid phases. So so the atoms of copper and silver have to like diffuse over to find their partners and then form up the phase. So there's a kinetic issue of them getting out of the way and then forming these structures, right? Equilibrium structures. So how fast can they get to those things? And it turns out that kind of dynamics ends up giving you weird looking things, like kind of tiger stripe morphologies. Right. So these things are like you take the metal, you slice it, polish it, do optical. These are optical images, like 5 micron. And you just can contrast the different phases and different, I guess, index of refraction or something. So anyway, I'm not sure if the phase diagram for this thing is here. This should be a complex phase diagram though, but let me show it. They show a eutectic in it, but I was searching for eutectics. I got these weird. Somewhere in here, there's some like really complicated phase diagrams. Let me just look for a second. Anyway, eutectic's the one, like if someone asks you questions, that's the one you absolutely have to know. Like just the steel phase diagram is pretty good, but I don't think I have it here. Not sure why. Before. That's complicated. Like usually they don't show the whole thing because it's so complicated, right? So it only goes to 0.667%, right? But you still have like, this is like typical. So you have all these little phases in here. So basically it's complicated, right? So you have like crystal to crystal. So you have like eutectoids and eutectics and all peritectics, and so there's all kinds of different transitions that are going on, different metal phases, metal crystal phases. Right, so this is an important one because it's like how you make steel. You put some little bit of carbon in the iron and make something nicer, right? Harder, less prone to corrosion, things like that. You put some chrome in, chromium. Anyway, so that's that. Actually, yeah, I know where that is. Let me just look for a second. Sorry. If you look like last year's homework, homework 5. That's a complicated phase diagram like that. Nickel alloy. So that, yeah, so you can see this is kind of a complicated phase diagram. So there's some things that, so some, you can see the straight up and down line, right? So that's the intermetallic. So it's like, it's as if you had, like that was another, in other words, you have a whole phase diagram between nickel and this intermetallic. That would be like a phase diagram. And then on the right side of it, you have another phase diagram that would be like zirconia and this intermetallic. And this, but this has 1, 2, 3, 4, 5 intermetallics. Those are things like stoichiometric, like CO2. It's a perfect match. It makes a perfect molecule. So you get that, and the free energy of that's like 0. So the free energy of these other phases is something, and that's almost 0. So you get, so that's like going to the ends, like nickel and zirconia. When they're pure, it's like almost 0. Like the free energy is 0 compared to the other mixtures, right? So basically, these things are like magic compositions where the thing clicks together. And then at that point, it's as if it's a pure component. Right. So the intermetallics are like all over the place here in this phase diagram. In this paper, they're doing laser powder bed fusion for like 3D printing. So you put the powder down, you cook it with a laser, and you see what comes out basically. Right. So anyway, you can imagine you can get a lot of different phase behavior in that situation. So they go through different compositions and like what this, then to determine like what comes out. So they create these phase diagrams with like CalFat or something, right? And then they go and make the stuff at that composition. So they do the kinetics and the thermodynamics together. It's a pretty good paper to do, but I picked a different one this year, you know. So anyway, so anyway, yeah, so then they do polishing and they get images of it and they try to determine what's in that. Like you can do it optically. You can also stick this in a TEM and determine the crystal phases, like what's the crystal phase and the composition, like EDX to get the chemical composition of each of the spots in it. So a lot of the analytic for metals is based on stuff like this, like trying to determine what phase is in equilibrium with whatever else stuff is in there and like how that thing grew. Like this is a pretty good example of the mess you can get into, right? And how you kind of resolve it as best you can. So it's kind of like this, in this case, there's also, so there's the thermodynamics, which is your roadmap. And then there's like the kinetics that decides actually what really happens, right? So the thermodynamic part of it, so you can see like, depending on what happens when you put this bead, when you go shoot the laser at the powder, you can get holes forming in it. That's not good. You want it to be solid. They can ball up instead of making a solid piece. It doesn't melt, then it's just still a powder. So you can see there's all these problems that happen because of the scan speed of the laser and the power that you put on the laser. So this is a kinetic mapping of like what happens. And so if you're doing some, take that kinetics and map it up with the thermodynamics, which is like this thing, and say what comes out as a combination of the two somehow. Like how fast did I melt it enough? Did I cool it fast enough? Did I get the phases I want? Right, so anyway, that's the ticket for that, I guess. That one's kind of good example of how things can get more complicated than this. But the eutectic's the one that is like a touchstone, like everybody has to know what it is. Right, so Lever rule, blah, 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 liquidus, solidus. That's liquidus. Solidus is when you get to the solid phase. So it's like that line. Invariant equilibrium. That means that you're going from this composition and you just go directly into the same composition of the two. Right. And then lever rule, tie line. That's it. Right. That's slide 1 of this stuff, which is like a few slides, but yeah.
The flat line between the pure copper and the pure silver, or not pure, but is that also a solid line?
I mean,
completely horizontal line.
Yeah, the eutectic line. Yeah, yeah, I guess it's a solidus line. I mean, usually like you're talking about, like someone will say in a paper along the solidus line, you know, that's when you use that. So say like, and then you know they're talking about like this line. So if they're talking about the eutectic, they would say the eutectic usually, but it is a solidus. So if it was a trick question, yeah, that's a solidus, I guess, you know. If usually in a paper if they were talking about, they'd be talking about like this line, you know. So anyway, so not sure how it's basically so you can like if someone's just it's terms of the trade kind of thing. So this guy's advancing here. There. So in the past I've given like a homework to use that, but you can play around with it. It's on the web page if you want to mess around. You can only do certain like you can only do like steel and solder. I think that's all with thermocalc at least. There's the free version. So like this is solder, right? So that's they have a couple demo examples. So you can't do like anything you want. Like you can't reproduce this silver to copper thing, which would be nice, but you can't. That's why I have solder here. So basically, you have to pay something. You see, mine have a license to CalFad. I don't know. Has anybody used it here? There might be a license for it. That if you, but you'd have to want to use it, you know. So if you want, you can probably get a license for it. Someone has it. Only Matt Steiner knows where it is, because I'm not a metallurgist. Yeah, yeah. Peyton might have it. I mean, somebody has it. Anyone that looks like a metal, ask them. You know, they can give you if you want to mess around with it. But the free version is okay too. I mean, to just kind of get a feel for what you can do. This is just showing like what you can get. So the eutectic you can get. It's like lamellar structures. I showed you a couple micrograph things. You get rods, get something called acicular, which are fibers, and you can get globular, which are basically like a spotted thing. All of them look like a leopard skin. And you do the micrograph of it. So basically you can tell when you went through a eutectic. It's going to be some kind of signature like that. Yeah, oh, here's some pictures of another paper. This is on the web page too, like just showing they're claiming they go through eutectic in these regions and they get looks like a tiger thing, so it's eutectic. Oh, this is another laser scanning thing. It's not the same paper though. This is 2020. That other paper is like 2022. Anyway, so yeah, I already kind of went through this business about following tracks along through the phase diagram. So the same thing happens with polymers. I mean, in a sense, you know, so polymers are always going to be, it's almost always going to be a liquid-liquid phase separation. So it's going to look like this simple, just a simple binodal, spinodal kind of thing, right? So again, actually, this is shown a lot better in that theme book. I was just looking at this, but anyway, this plot doesn't really do you much justice. Basically, this is going to be like a U here and a U there, and at the pit of the U is the binodal. So that's going to be the compositions for the binodal. This is at each of these curves is at a different temperature, and then the inflection point in between, like here and here, is a spinodal. So if you can see that's like a frown face, that means it's going to immediately separate. So if you get into this region, you have immediate separation. This part though kind of looks like a little smiley face on the edge. So that's like the single phase region. So that one is going to be metastable. Right, so that's this region D between the spinodal and the binodal. So this part is nucleation and growth. So in order to grow the phase, you have to overcome an energy barrier in that part and then grow the phase. It'll go to the binodal compositions. Same thing, the spinodal will go to the binodal compositions, but the mechanism will be different. Right, so spinodal, because it's spontaneous, you get composition growth up a gradient, up a concentration gradient. So if you so let's see. Yeah, let's see. So if you plot composition versus position, right, and you have nucleation and growth. So you have a nuclei, right, and then you have the average composition, and then there's a depletion at the surface, right, because it's growing this phase. So that means that you're going from this average composition to a lower, so your dCdr is like a positive value. Right, so you're driving the growth of that phase because you had a nuclei, and there's a depletion at the surface of it. So for spinodal, you don't get that. So spinodal, you start with these like fluctuations, right, and then the composition. So dCdr is negative. You got to grow the fluctuations uphill. Like if this is composition, this is position. You're moving material uphill, and it's going to grow like that. So you have like reverse anti-diffusion or whatever going on. Like it's going reverse. It's going against the concentration gradient. So all it is doing is enhancing these natural fluctuations that happen, growing the phases. So again, it's similar to the eutectic decomposition. In order for this guy to move up there, it has to diffuse. So there's a kinetics issue here, like diffusion, and there's a thermodynamic issue, like either the Hildebrand or the chi parameter. Right. So there's a thermodynamics that's driving it up the hill. There's a diffusion that's slowing it down. And then there's this, and the concentration gradient is negative. So the diffusion is really, here the diffusion is driving this in favor of the phase separation. Here it's like opposing it. So because you have a competition between the thermodynamics and the transport, then the spacing of these things becomes like a number that you can calculate. You get some kind of spacing of those that happens. It's a number you can calculate. So anyway, so spinodal again ends up giving you this kind of web structure that has some kind of spacing to it, thick spacing size. If you shoot a beam of light through it, you get a peak. You can get a spinodal peak that 2 pi over that angle gives you that spacing. And that spacing you can calculate for the diffusion coefficient and the chi parameter thing. Right, so anyway, that's that business. I think that's in the notes somewhere, but okay, so that's kind of how the polymer thing. So if you do a quench from A down here, then you're going to get this web structure forming. In the end, the web structure matures into domains. If you do this quench here, you get just domains, like it forms on the dust, right? And then this is liquid. And then I'm not sure what B is. Oh, right. This also superimposed on this, like if this is something that can crystallize, there's a crystallization temperature you can go through, and then you can get within the domains that you separated, crystallization happening in the domains. So it can get more complicated, but mostly it's just a simple kind of picture, like binodal, spinodal, and then just kind of quenching into the structure. So anyway, that's that business. Anyway, so the next part of this is like, where did these, like, how do you get like this phase diagram? Like, how do you generate that from our free energy? This one's simple. This is just the free energy, right? It's just a liquid-liquid phase separation. So you just have that equation. But in the case where you have like crystalline phases forming, not in this case, but if you have multiple crystalline phases forming, then you have this issue of multiple of these of this equation, like one for each crystal phase, one for the liquid phase, right? And they're all going to look the same, like they're going to have the same format. It's all going to be entropy, enthalpy. And so they're going to have basically this same kind of shape, like this kind of U shape, so that they're mixed better kind of in the middle, and the energy kind of shifts it around a little bit. But somehow there's a curve, right, for the solid and the liquid, two separate curves. So you can say like is it gonna be a solid or a liquid? Well, say I'm at 80%, I go up, which one has the lower free energy? The liquid, so it's a liquid at 80%. At this temperature, T3. So I'm at T3, I'm at 80%, I'm a liquid. This is a temperature composition phase diagram, right? And if I happen to be at 10%, the solid has a lower free energy than the liquid. So I'm at 10%, and I'm at T3, I'm a solid here. Right, but if I'm right at this composition like 32, then I'm right at this spot. So if you take the slope of the free energy versus composition, that's chemical potential, more or less. And the chemical potential of this guy and this guy are equal to each other at that composition. And in between these two, those two things continue to have the same chemical potential. So that means that if I put in this 35, it's going to separate into like that phase and that phase. Right, so that's where I'm in between these two things, and that circle are these 2 points on the free energy plot. So you have still this simple free energy, you just have one for each of the phases that you're looking at. Right, so basically you can construct this kind of simple liquid solid. So this is a solid solution, so that this is silicon germanium, so they're both diamond cubic. And they're about the same size. So just like one step away from each other in size. They can make a diamond cubic crystal all the way across from 0 to 1. And it's randomly mixed germanium in the silicon. Right, so it's just one crystal. Right, and if you heat it up, it melts into one liquid. It has the same composition. But if you heat it up, where you have this scenario, so if you're between the gap of these two at T3, then it's going to separate into a solid and a liquid of 2 compositions. One's mostly germanium liquid, and one's mostly silicon solid. Right, so you have a solid and a liquid in equilibrium with each other in this region. And as you change the temperature, these two equations have different temperature dependence. In other words, the enthalpy term is different. Right, so basically that's going to generate different curves for different temperatures, and they'll change kind of shape at different temperatures. And the way they change shape, it maps out like this is, let's see, is this also, oh, these two are the same, right? This is just showing, if you're in the dilute or the dilute, you have a lower chemical potential for the liquid. You have a lower free energy and lower chemical potential for the liquid in here. Anyway, so it works out with the chemical potentials too. Anyway, so that's kind of how you do it. You use the same equation to get these curves, and then from those curves you can generate the phase diagram. Right? So that's kind of the idea. How you get this thing and that thing. Like we saw, like this is pretty simple. It's just one equation. And it's all liquid. And then this is 2 phases, liquid and solid. And then you have 2 curves, the solid and liquid mixing. And that can generate this. So that's kind of the theme of this chapter, is just how you can construct these complicated phase diagrams from free energy plots. So this is just showing, this shows all the different temperatures, like T1, T2, T3, T4, T5, how the curves differ. So when you're at T3, you can get the 2 phases. When you're at T2, liquid is always lower free energy than solid. So T2 is always liquid. T1, liquid's always lower than solid. So T2 is where they cross at 0. That's where that point is. And then T5 is where they cross at 1. And then T4 has 2 phases. So it's the same thing. There's a slope here that will give you the 2 points on T4, the 2 points on the phase diagram. So you can see it's just the same kind of free energy curve. It's just the temperature dependence is different for the solid and liquid, and that generates a phase diagram. That's how this thing works. Anyway, why don't we can kind of leave that here, I think. Probably enough stuff for now. Yeah, so we'll get all these. They kind of go through how to get up to the eutectic. Like we can get this is like a simple solid liquid equilibrium. This is called congruent melting. Then that's eutectic. And then if you did solution thermodynamics, it's like chemistry or chemical engineering, you didn't see any of these. But what you saw was like you saw basically this liquid, and if you had liquid vapor, so liquid is kind of like chemistry, I guess. Liquid vapor is like distillation for chemical engineering. When you do that, see there's the same things, what they call them, something ideal is called ideal. This is liquid vapor, LV, this is liquid solid, SL, right? But the phase diagrams are kind of the same, right? Then this is called an azeotrope. So that's like alcohol and water has an azeotrope, so you can only purify it so much. That's why you can only get like grain alcohol to 90% or something. Right. So basically there's a point of no return. So these lines are following like a distillation column, each stage in a distillation column. So that azeotropes are the same as a congruent melting for liquid solid is vapor liquid for an azeotrope. So azeotrope is the most popular chemical engineering phase diagram, just like eutectic's the most popular materials phase diagram. But azeotrope and congruent melting isn't very popular in materials, but azeotrope is really popular in chemical engineering. Right. So basically, because if you're distilling two components, this is your dead point that you can't purify it anymore. Then you need to use like membrane separation or some other thing. You're stuck there. Or you can put in a thing put in a third component to what they call break an azeotrope. So you can get to more pure. So you can see like they've engineered a lot around this thing. Whereas this is kind of like the bread and butter for like it's in the steel phase diagram. It's kind of like everywhere. Just the reason that this term is so popular, this congruent melting isn't something you'll see much at all. So then the heteroazeotrope you'll almost never see because it's way too complicated for any chemical engineer to look at. So they try to make it look like an azeotrope if it is a heteroazeotrope. So you have two liquid phases that are immiscible with each other. And then you have and here you have two crystal phases that are immiscible. You end up with kind of the same phase behavior. So heteroazeotrope you'll never hear of, and then eutectic is like the bread and butter. So it's kind of funny, like no one ever says this, like mentions that the two things have direct parallels. Just three different fields of science, and they don't really talk to each other much. But it's kind of the same stuff. They use the same. In the end, they're all going to use the Hildebrandt to construct these things. So it's kind of the same thing. Anyway, I thought I'd mention that. But polymer is almost always like this phase diagram, and metals is almost always eutectic. And these guys are always azeotropes. So anyway, let me quit there. So I'll try to finish this chapter tomorrow. There's not much more. I mean, it looks like there's a lot, but there really isn't much more. And then go through the homework for this week. And then, so hopefully that'll work out. Any questions or anything? But, all right, good. All right, let's quit. Let's shut this guy off.